Here's another triple integral where it makes sense to go ahead and utilize a coordinate system that we've already discussed. Like in the previous problem, we talked about spherical coordinates. Here we're going to use cylindrical. So what we want to do is compute the volume of the solid bounded by this particular paraboloid, that is z equals 16 minus x squared minus y squared, and the xy plane z equals 0. So this has like the gumdrop shape. Notice the ceiling is the paraboloid, and the floor, z equals 0, is just this blue shaded part. So very similar to the last problem, but we have to attack it in a little bit different way. So now when we think about the z equals 0 disk, we see that x runs from -4 to 4, then y will run from the negative square root of 16 minus x squared to the positive square root of 16 minus x squared, and then of course z runs from the xy plane 0 to 16 minus x squared minus y squared. Now again, like we did with the last problem, let's go ahead and look to see what the actual Cartesian integral would look like. So again, we would do the triple integral of the volume element, dz, dy, dx. Now when you look at this, again, we have the x limits, -4 to 4, the y limits, the negative radical to the positive radical, and then of course the z limits, 0 to the paraboloid, 16 minus x squared minus y squared. Now again, this integral would actually be quite difficult in the sense that we'd have a lot of Pythagorean integrals to compute, which would be unnecessarily difficult. So since we already know the cylindrical coordinate system, let's just remind ourselves. For instance, if we want to describe this gumdrop, so to speak, again, we're going to think polar in the xy plane. So theta would run from 0 to 2 pi, and of course r would run from 0 to 4. And now, of course, z is actually equal to z, but any opportunity to replace x and y in terms of polar, we take advantage of. So for instance, the z would be 16 minus r squared here. And so basically when you think of the Cartesian coordinates written in terms of the polar, you have this. So it's polar here and z equals z. And then of course, because of that, when you do the Jacobian, the absolute value, you just get r, just like polar coordinates. So there's not a whole lot of additional difficulty here from the polar integrals that we did in the previous sections. So now, when we take the Cartesian over to the polar, we have a very simple process. Again, the new volume element, as we've seen here, gives us this Jacobian. So our Jacobian turns up here in the volume element. So we have r dz dr d theta. And then, of course, the limits on theta 0 to 2 pi, the limits on r 0 to 4, and then of course the limits on z 0 to 16 minus r squared. Now notice these two integrals involve the r, so they're related, but the theta integral is very simple, so we can pull it off to the left and just compute that. Now of course, since the z integral here, there's nothing, any z in here, so basically this is just z from 0 to 16 minus r squared, so that simplifies really quickly. So we just get 16 minus r squared r dr for the r integral 0 to 4, and then of course the theta integral, as I've already discussed. So now as we move forward, we want to make this table ready. So of course from the chain rule we need a -2r, we don't have that, so we put in the -2 and then compensate. And then of course, this integral is just 2 pi, and this one's ready to go. So we're thinking of this as the u, and this is the du. So we add 1, divide by the new power. So we have, in this particular case, a negative pi. Again, the 2's absorb, and then when we add 1, divide by the new power, we get 16 minus r squared, quantity squared, divided by 2. Now at this point, we just have negative pi over 2, and evaluating at the upper and lower limits, the upper limit gives us a 0, the lower limit will just give us 16 squared. Now the negatives absorb, we get pi over 2, 16 times 16, 2 into 16 is 8, 8 times 16 is 128, so we get a volume of 128 pi. And let me assure you, the integrals that would ensue in the Cartesian would be very time consuming, or you would be busy using a table of integrals. So we see that in cases of double and triple integrals, new coordinate systems can be very, very useful in saving us time in computing these integrals. And we are done.